All right. We've talked about how do we do multiple linear regression and how do we use the pattern of the residuals to check if there is any problem. But there are two conditions you have to meet in order to make inference that how the model was wrong. But in general, it can tell you by looking at the standardized residual, it can tell you whether it's a valid model or not. So now we'll talk about another tool to check if our model is valid, our multiple linear regression model is valid or is adequate or not. So this marginal model plots, they compare the least square regression fit to a non-parametric fit. So non-parametric fit is you can think it as there's no parameter involved, so there's no beta 1, beta 0, beta 2, those kind of things to estimate for that fit. So it would be a curve. And it has really high degree freedoms. That means it's highly flexible. So a curve. And often we just use this LOIS, which is locally estimated scatter plot smoothing. So this is a long name, so people just use LOIS for it. I don't remember who called it as this full name, but just in case if you are curious. So we compare the least square regression fit, our multiple linear regression, with this non-parametric LOIS curve. And we will decide the regression model is a valid model if this like two fit agree. Like when we plot them out, we would see two lines and we check if they agree or not, so that we can make the evaluation about our model. But the difficult part for making this marginal model plot for multiple linear regression is that we have to plot it for each predictors. So for if we have only one predictor, as in simple linear regression, well, we just compare like the non-parametric curve, LOIS curve, with your regression line. But now we have more than one predictors, and we have to do it for each of them to make a plot for each of them. Well, the idea behind the marginal model plots is based on rate condition expectations. Well, it involves lots of conditional expectations on the predictor. Well, if you are curious, you can look into the textbook, find out like the theory behind it, how that we could just compare like the expectation of this y given x1, for example, if we consider x1 at this moment, and comparing this one with, the non-parametric estimates of this to this expectation. For x2, x3, it's the same. We are comparing a non-parametric curve with this expectation, which is estimated for your model. And we will call this one the non-parametric estimate of this. We would call it, it's fitted for the data. Let's take a look at an example where you will have a better idea of what it is. So we'll still use this defective rates example that we talked before. And remember we have y response variable, the y being the number of defective. And the one predictor we have is a temperature. So well, we have plotted here. This is the y-axis and number of defective. This is the predictor temperature. So in this line, so by the way, this is one marginal model plot for this temperature. Let's see, x1 is our temperature. So this solid curve is, you see it is a curve, is fitted to your model. So this is, it's fitted to your data. So according to where the data is located, you just get this non-parametric line fitted to the data as close as possible. So this is what it looks like, this solid blue curve. And this dashed red line is the estimate, is your basically your model. So the model we're considering here is, it looks like a linear model, right? Just regress this y on this x1 temperature. Well, we just compare these two lines, the line fitted to your data and the line from your model. So if they do not agree, just like in this case, we are confirming this model is a perfect, this linear model. Just regress y on x1. It's not a good idea. And we eventually transform this y by taking its square root, if you recall that when we talk about transformations. And I have this marginal model plots for like before the transformation of y and after the transformation of y. Notice that I have the plots for each of the predictors. So x1, x2, x3, and this is like the eventual final check comparing your y, like you regress the y on y hat. Remember when we do the transformations, our last step would check if the transformation is adequate. So yeah, this is the marginal model plot, and so how do you get those? So if you use MMP function, you can get like the marginal model plot for one variable. If you do MMPS, it would do the whole set. And let's take a look at all the plots. So on the left, results transform y. You can tell that the lowest curve, the non-parametric curves, the blue curve, are not really matched with the red line, which is like fitted for the model. So this is the indicator. It's not a good fit. And after the transformation, we transform the y, right? And they agree much better, right? So this give us the confidence that this model is good enough. So this marginal model plots is helping you to make sure the whole model fit is good by just comparing your model with the non-parametric curve fit to your data. Well, you might ask, why don't we just use a non-parametric curve, like the lowest fitting, to your data? Well, it's like when you do a non-parametric fitting, it's hard to make inference, right? Like it's hard to interpret. So when you do a non-parametric fitting, non-parametric model. So that's kind of the advantage of we have this multiple linear regression and single linear regressions, and we have specific interpretations for those coefficients. Remember, like we can infer, like we increase the x, how much the y would increase. But for non-parametric models, they are more useful when we are like purely just want to do predictions. So they have different strengths. And we just use this non-parametric model as kind of a guideline to see if our multiple linear regression model is good enough or not. So that with a valid model, then we can make our interpretation, then we can make our inference. right? Well, the next topic which is a quite important topic in this multiple regression models. It's called multicolinearity. And I mentioned this a couple times, but let's just formally look at it. So strong correlations between predictor variables is known as multicolinearity. So if you see like high correlated predictors, you will know this model would have this multicolinearity problem. And its presence can cause lots of issues, such as the regression coefficients that you estimate would have the wrong sign, or many of the predictors are not being significant, while the overall F-test might be highly significant. So that's a bit strange, right? The F-test is telling you the overall model is really significant. But if you look individually, your predictor variables, maybe many of them are just not significant at all. And you can even get very surprising sign, like the increase or decrease according to the predictor's increase or decrease. Sorry, I mean the increase or decrease trend if we change the predictors. But I think it's better that we just look at one example to illustrate the problematic model. We have multicolinearity. So let's get to oh, this is strange. I think I didn't share the screen. Let me stop share for a moment and get a new share. New share screen. Okay, well, hopefully you now can see this example from Armada. Like this is the bridge construction example that I took from the book, and we first read the data in and do a scatter matrix plot, scatter plot matrices, or either way. Well, by the way, some people or some students saying this pairs function is not working so well. If you put the whole data set, just use the dataset name as the arguments for this function. But for some it worked, but for some others on their computer, it will not work, and probably give you an error that says non-numeric value to this pairs function. Well, we couldn't figure out why like it worked for some of the R version and some and pops error for others. I think maybe it's better that you just use these formats when you do this pairs plot. So you know you want to put this y variable, response variable to the very top, and you kind of plot it versus this many predictors. So this is more clear that what variables you want to plot. So anyway, you can figure out how to make this pairs working. So just by looking at this scatter plots, we can tell there are like non-constant variance, like for when you plot the response versus each of the predictions, and they are highly skewed data, and so that they kind of squish into this corner of zeros. So let's look at what a Box-Cox transform suggest, and we do this power transform with our response variable and all the predictors. So this is the multivariate box transformation. So this is for estimated lambda to do the transformation. And this likelihood ratio test is testing if all the lambdas should be 0 or not. So this null hypothesis for this one is saying all the lambdas for this variables should be 0. And we got a fairly high p-value. So we fail to reject the null hypothesis, and we can conclude that, well, we can conclude that, it's suggesting us to do log transformations for both y and x's. Logs all around. So let's do a new pairs plot with transformed variable. Just for comparison, I plot this again here. This is original before transformation, and this is after transformation. And this is how you do the plot. You just directly do the log of each one, and it will show you after log transformation. It's much better, right? These relationships are becoming more linear related. And the non-constant variance issue and the skewness is kind of removed. So let's just build a model with these new variables, plotting this, and also plot the standardized residuals to check it out. Again, this is just as usual. How do we get the new model with the transformed data and get our standardized residual and plot against the new variables? And so it's like fairly random, and there's no particular pattern associated with the residuals. So we can conclude it is a valid model. Now, this is kind of a review of what we do in general for a multiple regression model. And inverse response plot, again, confirming this is a valid model. If you plot the new y and the y hat, it's pretty linear. And then some diagnostic plot confirming this is good, or this is all the information I'm giving you. This seems like a valid model, right? And if we look at the summary of the regression output, and we notice this is the highly significant model overall by looking at this F testing p-value. But if we focus on those individual variables, the transformed variables, many of them, we could see only one of them being significant and all others are not. So as I summarized here, well, it makes no sense that larger area, see, this is for the area, the variable for area. So this is kind of an example of you got wrong sum. So in this case, it makes no sense that the larger area and larger lengths would take less time for building a bridge, right? By common sense, we would know if it's a bigger bridge, well, it takes longer. So we can confidently say that the coefficients are the wrong sum. So this is something really you have to pay attention before you present your results to your manager or to your coworker, to your advisor. So this would be ridiculous, right? So let's see what's happening. Because we are talking about multicolinearity, right? We kind of know they are, and we can check later, they are highly correlated. So when two or more highly correlated variables are included in a regression model, and because they both or they all contain similar information about the response variable. So the linear model of least square, the method that the least square method that we use to estimate our coefficients here, it cannot tell which effect is due to which variable. But it knows the model is highly significant, but it cannot distinguish like which variable is contributing more than others, like which variable is more significant. So it just cannot tell. Yeah, even though the model is not highly significant, but the variables will not all be significant. And this would also give us the opposite sign than we expected. Like, for example, on this area and length variable. So, well, I put this, how do you do the marginal autoplots? It shows you, even though there is a bit curvature, but on the book, it says we shall continue under the assumption that the model is valid. So they are not like perfectly matched, but they are close enough. So that's not that a big deal. So it's close enough. And then you do added variable plots like this. And this is how you like arrange those variables. It will be 2 by 3, so 2 by 3 kind of matrix. That is how you arrange those plots. And yeah, we know how to check this added variable plots. And you can see that the line for joining is steeper. The line for joins is, I think this one is steeper than all others. It's backing up how it's only significant, the only highly significant one. And the line for spans is somewhat steep, or the variable has the smallish p-value, which is just over 0.1. And this is what I'm talking about. This is highly significant. This is close to significant. And this added variable plots is kind of backing up about their p-values. Well, let's take a look at how correlated are these variables. And this is how you get their correlation. You first kind of rename them so that it's easier for you to combine them into one data frame called X. And then you do the correlation of this X. So this function will pop up the cross correlations for each of the columns you have in this data frame. And just by looking at the correlations, they are really highly correlated. Yeah, so that's how you see the negative sign, I mean the wrong sign, and highly significant model, but not many significant variables. So this multicolinearity is troublesome. You have to pay extra attention when you do these multiple regressions. Okay, let's, whoops. Yeah, I need to get new share again to back to our slides. Okay, this is related to multicolinearity. Various inflation factors. You will be able to understand a bit further why the multicolinearity is causing that problem that we saw. So let's look at multiple regression model with two predictors, X1 and X2. And if we denote the correlation between these two predictors as R12, and it can be shown, we can write the variance of the estimate of the coefficients for xj, which is called beta j hat, coefficients of xj, and it's beta j, and this is the estimate of beta j hat. So the variance of this estimate can be written as a function of this R12. So j can be equal to 1 or 2 because we have two variables, right? You can tell from this you can tell the variance of the coefficients will be larger if we increase this R12. Right? If this increase, this denominator would decrease, and then the whole thing would go up. So, for example, if we know the R12 squared being 0.99, and then the variance of the coefficients, if we do this calculation, just calculate this first term, it would be like this. You plug in this. Oh, sorry, I should have removed this square. Well, anyway, so this term would equal to 50.25. That means when R12 square being 0.99, this variance of this coefficient would be 50 times larger than it would be if R12 square being 0. Right? When R12 being equal to 0 is just 1, but this one is like 50.25. So it's 50 times larger. So this gives us the hint how like the variance of your estimates, of your coefficient estimates is big. That means the standard error is big. So we have very much lots of uncertainty when we do that estimation. Well, in general, let's define this variance inflation factor. So if we consider this multiple linear regression as few predictors, and we again use Rj squared to denote the value of R square obtained from regressing xj on other axes. So this is giving you this Rj squared, is giving you the amount of variability of xj that can be explained by other predictors. And so in this general case, we can again write this variance of beta j in this way. So this becomes Rj squared. And this first term here is known as the variance inflation factor for xj. So this corresponding. So for our example, like the Brady example, a number of these variance inflation factors. By the way, so this is how you get the VIF. You just put the model in, it will give you the VIF for each of your predictors. So many of these variance of the VIFs would exceed 5. And this is the cutoff often used to determine if the coefficients are poorly estimated. If it goes up, if it exceeds 5, we will see these coefficients are poorly estimated. So you have to be really careful if we use their coefficients to do like interpretation of the model. So that can be easy to make mistakes, like silly mistakes. Yeah, so we just use this OVIF to kind of as a deadline to see if the coefficients, if we are experiencing this multicolinearity problem, and also we check the correlations, cross correlations among predictors to make sure if just to check if we have this multicolinearity problem, and pay extra attention so that when you do multiple linear regression. Yep, that's it for this week.